Introduction. Greetings, students. Today, we embark on an intriguing journey into the world of data structures, focusing on a fascinating challenge known as LeetCode Problem 19, remove nth node from end of list. This problem invites us to manipulate a linked list, a fundamental structure in computer science. We are presented with the head of a linked list and an integer, n, which signifies the position of the node we must remove, counting from the end of the list. For instance, consider the linked list represented as 1, 2, 3, 4, 5, with n set to 2. Our task here is to eliminate the second node from the end, which in this case is the node containing the value 4. Upon removal, the modified list transforms into 1, 2, 3, 5. As we delve deeper into this problem, we will explore the traversal techniques and underlying algorithms that allow us to achieve this elegant operation. The two pointers technique is a powerful algorithmic approach often applied to problems involving arrays or linked lists. Imagine you're trying to find a specific item in a long line of people. Instead of searching one by one, you can send two friends down the line, one moving slowly while the other moves faster. This allows you to cover more ground efficiently. In programming, this technique involves using two pointers that may move at the same pace or at different speeds, depending on the problem's needs. By doing so, we can often avoid nested loops, which helps us improve the time complexity of our algorithms. The beauty of the two pointers technique lies in its ability to simplify complex problems. For example, by adjusting the pointers based on specific conditions, we can quickly narrow down potential solutions, like finding pairs of elements that meet certain criteria without redundant checks. As we implement this technique, we start by positioning the pointers strategically within the data structure. This dynamic movement allows for a more streamlined exploration of the data, making our approach both efficient and effective. In this example, we'll explore the two pointers technique using a function designed to find pairs in a sorted array that sum up to a target value. We start by initializing two pointers, the left pointer at the beginning of the array and the right pointer at the end. This setup allows us to efficiently search for pairs that meet our criteria. As we loop through the array, we calculate the sum of the elements at these two pointers. If the sum matches our target, we capture this pair in our result list and then move both pointers inward. If the sum is less than the target, we increase the left pointer to try a larger value. Conversely, if the sum exceeds the target, we decrease the right pointer to find a smaller value. This method continues until the two pointers meet, ensuring we efficiently explore all potential pairs without unnecessary comparisons. Finally, we return the list of pairs we've found. This approach is both intuitive and powerful, allowing us to solve problems with ease. The slide presents a basic structure for a linked list using a node class. Each node represents an element in the list, containing data and a pointer to the next node. This is crucial because linked lists are not stored in contiguous memory locations. Instead, they use these pointers to connect nodes. Next, we have the traverse linked list function, which allows us to navigate through the linked list. We start with an empty list to collect values. The traversal begins at the head, or the first node. As we move through the list, we append each node's data to our values list. This process continues until we reach the end, indicated by a none pointer. The function then returns the collected values, giving us a convenient way to see what's in our linked list. In our example, we create a simple linked list with 3 nodes containing the values 1, 1, 2, and 3. When we call the function, it will return a list with these values, demonstrating how the traversal works. Node reference manipulation is a key concept in computer science, particularly when working with structures like linked lists, trees, and graphs. Each node in these structures holds data and references, or pointers, to other nodes. By manipulating these pointers, we can change the structure of our data. This includes tasks like adding, removing, or rearranging nodes. Understanding how to manipulate node references is critical for efficient operations. For example, when we insert a new node into a linked list, we need to adjust the pointer of the previous node to point to the new node, while also making sure that the new node points to the next one. This careful adjustment helps maintain the integrity of the data structure. However, it's crucial to handle these pointers with precision. Incorrect adjustments can lead to memory leaks or other issues that compromise our data structure. By mastering node reference manipulation, you'll not only optimize your code, but also gain deeper insight into how data structures work. This slide introduces a simple node class, which is essential for creating a linked list. Each node holds a value and a reference to the next node in the list. Think of it like a train where each car represents a node, and the connections between them are the references. In the Manipulate Node References function, we begin at the head of the list. As we traverse through the nodes, we double the value of each node. This is done using a while loop that continues until we've reached the end of the list, which is indicated by a none reference. The example usage shows how to create a linked list with 3 nodes, holding the values 1, 2, and 3. By calling the Manipulate Node References function, we alter the values of these nodes, demonstrating how we can manipulate node references effectively. This process illustrates not just how to create and traverse linked lists, but also how powerful node manipulation can be in data structures. LeetCode problem 19 focuses on removing the nth node from the end of a linked list. Let's break this down step by step. First, we define our problem. We need to find and remove a specific node from the end of the list, and to do this efficiently, we'll employ a 2-pointer technique. Next, we choose our data structure. A singly linked list is ideal for this problem, and introducing a dummy node helps us manage edge cases, like when the head needs to be removed. Now, we initialize our pointers. Both the first and second pointers start at the dummy node. Then we advance the first pointer n+1 steps ahead. This positioning is crucial because it sets us up to find the correct node to remove. As we traverse the list, we move both pointers forward until the first pointer reaches the end. At that point, the second pointer will be positioned just before the nth node from the end. Now, to remove the node, we simply adjust the next pointer of the second node to skip over the nth node, effectively removing it from the list. Finally, we return the modified list, starting from the node after the dummy. This method ensures we only traverse the list once, maintaining efficiency. By using a dummy node and the 2-pointer technique, we simplify our solution while achieving OL time complexity. This is a clear example of how effective pointer manipulation can be in linked list problems. In this problem, we are tasked with removing the nth node from the end of a linked list, returning the modified list's head. It is crucial to consider edge cases, such as an empty list or when n is equal to the list's length. Notably, the linked list can contain between 1 and 30 nodes, with values ranging from 1 to 100. This constraint on n ensures we will always have a valid node to remove, guiding our solution strategy effectively. The provided Python code addresses LeetCode problem 19, which focuses on removing the nth node from the end of a singly linked list. This solution uses a 2-pointer technique, which is an efficient way to manipulate linked lists. By employing this method, we can achieve the desired result in a single pass, optimizing both time and space complexity. We start with the listNode class, which represents each node in the linked list with a value, val, and a reference to the next node, next. In the remove nth from end function, we create a dummy node. This dummy acts like a helper, making it easier to handle cases where we might need to change the head of the list. Next, we utilize two pointers, first and second. The first pointer moves ahead by n+1 nodes. This offset ensures that when first reaches the end of the list, the second pointer will be perfectly positioned to point to the node just before the one we want to remove. We then traverse the list until first is at the end. Once we reach the end, we simply adjust the second pointer's next attribute to skip over the nth node, effectively removing it. Finally, we return dummy.next, which may point to a modified head of the list. This algorithm operates in OL time complexity, where L is the length of the list and it uses O1, additional space, exemplifying an optimal approach to handling linked lists. The time complexity of removing the nth node from the end of a linked list is ON. This means that we need to go through the list twice, first to determine its length, and then to find and remove the desired node. Think of it like counting the number of students in a line before picking out the one who's standing in a specific position from the back. Now, regarding space complexity, it's O1. This indicates that we use a constant amount of extra space, regardless of how long the list is. For example, if you were organizing books on a shelf, you might only need one additional bookmark to keep track of where you are, no matter how many books you have. Thus, the only extra space we use here is for pointers to help us navigate the list. This efficiency makes our approach both time and space effective.